We've looked at those net force problems in a horizontal or a vertical direction where we're only moving in one dimension. And so now what we want to do is we want to look at what happens when our object is not just moving straight horizontal or not moving straight vertical. Okay, so we're actually looking at an angle of 35 degrees. We have a block. Let's just say for now that there's no friction. And so we have this block that's being pulled up by some tension force up this incline. And a nice simple thing to find would be maybe the acceleration. So let's say, what is the acceleration of this block? That I can't spell. Acceleration. All right, so we're going to try to find the acceleration of this block. So kind of a list of things to do when you have a problem like this. Okay, now the first thing that we want to do is we want to identify the forces. We're talking about this block, and we want to know the acceleration on this block. So the first thing that we want to do is identify the forces. Okay, so what forces are involved on that block right now? So we have our block. Okay, and we always know that Earth is over here. And we've got this force of gravity acting on the Earth. We obviously have a tension force right here, whatever's, I don't know, you, maybe you are up here pulling this block. There's a force of tension acting on that block. And then we are sitting on a surface, so the incline, whatever our incline is made of, okay, is supplying a normal force. So looking at that right there, we can see that there are three forces acting on that block. Now we want to use these forces and we want to draw a sketch of that situation. Okay, so now that we know what forces there are, we want to draw the vectors on there. So we're going to sketch some vectors. We're going to draw a force diagram. So here is our block as a block. Okay, now we want to actually just take our picture and draw that. So I'm a big fan of straight lines. So I'm going to bring my ruler and I'm going to just draw this force of gravity is pulling down. Okay, so anytime that we draw a force diagram, we are going to draw that gravity acting down. Now we have a tension force acting at a 35-degree angle. If you wanted to, we're just sketching this, if you wanted to, you could actually measure out that angle with your protractor. We're just going to kind of estimate that. Here's kind of a tip. If this is parallel roughly to this, that's a pretty good estimate. And we know that this force of tension is 150 newtons. That was a given for us. And then we also have our normal force. Okay, so now our normal force acts perpendicular to the surface. So the normal force is going to be perpendicular to this tension force right here. Okay, so this is a right angle. Okay, so now that we have our force diagram drawn and our forces identified, we want to resolve this into x and y coordinates. We've been doing that, right? We've been talking about something moving in this direction. We have those horizontal components and those vertical components. We're going to do the same thing. Now the great thing about our coordinate system is that we can define that however we want. We can say that straight up and down is our y-axis and straight across is our x-axis. But if you notice what will happen here, if we define this as straight up and down, we're going to have a vertical component for our normal force, and we're also going to have a vertical component for our tension force. That will also mean we have a horizontal component for both of those forces as well. So the only force that would really line up with a straight up and down coordinate system is going to be our force of gravity. So the thing is, we can define our coordinate system in any way. And a lot of times it's going to be helpful to define it in a direction with our acceleration. So what that means is we're pulling this object up here. We've got our tension force, and there's nothing acting in that direction. If we keep it like this, our acceleration has an x and a y component associated with it. But if we tilt our axis just a little bit, let's just say that this right here is our x-axis. Perpendicular to that then is going to be our y-axis. Okay, now see what happens there? Now what we have, our tension force falls right along that x-axis. Our normal force falls right along that y-axis. We don't have components for those two forces. Now the only components we have are our gravity. There's only one of them. So defining our coordinate system in a way that lines up with our acceleration. Okay, so our acceleration now is going to be along this x direction. That's how we can define that. Okay. Now what we want to do, we want to resolve this. Here we've got, if we draw a little line here, now a little line here, what we have here is we have a force of gravity in the y direction. Let's make this a different color. And the force of force of gravity in the x direction. And you'll see why I did that here in a minute. Okay, so now our gravity has an x and a y component. We can draw a straight line across so that we make a right angle with our y-axis. Okay, so now what we want to do is identify all of the forces acting in each direction. And this is called the sum of the forces. So this Greek letter sigma, what we want to look at is the sum of the forces in the y direction. Okay. Now if we look at everything that is moving up and down, or all the forces that are acting up and down, we have the normal force, and we have the y component of our force of gravity. Okay. Those are the only two things acting in the y direction. Now if we look at our x, okay, and the sum of our forces in the x direction, okay, so sigma fx, we have our tension force in our x direction, and we have the gravity x component. Now remember, by tilting our coordinate system, what we've done then, we can't have an acceleration at all in the y direction. Because we have this normal force pushing up and we have gravity pulling down. If this is what we define as our y, that block isn't going to float off and it's not going to come down into the surface of that incline. So we don't have any net force in the y direction. So the sum of the forces, the normal force plus the y component, is 0. We are balanced in the y direction. Now if we look at our x direction, we defined this. This is the direction that our acceleration is occurring, right? So now what we've got is we've got this force pulling it this way. That's where that acceleration is occurring. So this is not equal 0. So I guess this is step 2, right? We have defined our coordinate system. So we've got this coordinate system. And we have used that to resolve our vectors. So that kind of goes along with this. So define your coordinate system and resolve your vectors. Okay. So that really kind of helps. And then over here, I guess you could make this a step 3. Well, you could sum your forces. Okay. So in order to find our acceleration, what we need to do is look at the forces that are acting in our x direction, right? So since our coordinate system now is going in the x direction, that's the direction that our acceleration is going in, only those forces going in the x direction are going to be affecting our acceleration. So we want to find those, which is kind of nice because we've got, this is, I guess, step 4, right? So step 4, determine the net force. Because our acceleration depends on our mass and our acceleration. Or our acceleration depends on our mass and our net force. So our net force is in the x direction. This is our net force right here, this tells us what our net force is. We don't know what it is. That's what we're trying to find, right? So the forces in our x direction, our tension force and the x component of our gravity, are the forces in our x direction. Those added together is the net force in that x direction. So we know, let's see, so force of tension plus the force of the x component of our gravity gives us our net force. So that's what we're trying to find. Well, we were given our tension force. Okay, so this is 150 newtons. That's kind of nice. And we can find our x component. We can find gravity, right? We can always find gravity. Gravity is mass times the gravitational constant. So we can always find this. So mass is, what is mass? Mass is 15 kilograms. And we're going to multiply that by 9.8 newtons per kilogram, which is a negative. So what this tells us then, well, let's do the math. I don't know what it tells us. So if we have 15 times 9.8, we're going to have a force in the x direction, or a force in our force of gravity. This is our force of gravity, not in the x direction. This is our force of gravity is going to be negative 147 newtons. Okay, so that tells us this right here. That's what this is telling us. And we want to know the x component of that. Okay, so the angle of our incline is 35 degrees. And so if we were to draw this angle right here, this is our theta, this is our angle that's going to match up with that 35 degrees. So this is going to be the opposite over our hypotenuse, which is our sine function. So the g component, the x component of our force of gravity, is going to be that negative 147 times the opposite, which is sine of 35 degrees. So that gives us the x component of our force of gravity is negative 84 newtons. Now it's negative. If you think about that, here's where our positive is going. If we define this as positive, our x component is going in the opposite direction, so that does make sense that that would be negative. So what we're going to do is we're going to come back over here with this, and we're going to add that in, and we get a net force. Let's see, 150, do this right, is going to be 66 newtons. So the net force acting in that x direction, actually the only net force that we have, is going to be a positive 66 newtons. So then what we're going to do, okay, so our net force is mass times acceleration. So positive 66 newtons is going to be equal to our mass times our acceleration. So to solve for acceleration, we're going to take our net force divided by our mass, and we're going to get 4.4 meters per second squared, and that is a positive. Now what happens if we have, let's get a new piece of paper here. What happens if we have friction? Let's just say that we have a friction force of, I don't know, 25. Is 25 a nice number? Okay, let's say we have a friction force of 25 newtons. So over here, we didn't have a frictionless, we had a frictionless surface, so we didn't have any friction to add in there. But now let's say that we do. All right, so this is going to change a little bit. We can come back to our forces. Okay, so here's our box. We've got Earth over here with our gravity. We have U supplying some tension force. Then we have our incline, and our incline is providing two forces here. Okay, the first thing we still have that normal force from our incline, but our inclined surface is also supplying friction. Okay, so those two surfaces going together, you're going to have some friction on there. Okay, so these are the forces that we've got. So when we look at our box, we have 4 forces now. We look at everything that's surrounding that box. Anything that touches that line is going to be a force acting on our box. So we're going to draw our force diagram, just like we did before. Okay, so we've got gravity coming down here. We're going to go at our roughly 35-degree angle with our tension force. Now we also have, if our block is moving in this direction, our friction is going to be moving in the opposite direction. So our friction is going to be going in that direction as well, probably not quite as much. So we have friction going this way. We have our tension force going this way. And then our normal force that way. So this is the force diagram if we include friction. Okay, so here it was before. I mean, it looks the same. The only difference is now we've got friction going in this direction. Now you can really see where it's kind of handy to have that coordinate system going in this direction. So now what we've got, okay, so here's our coordinate system. I'm just going to draw it like that. And like this. So this is our y direction, and this is our x direction. Okay, so we've defined our x along this axis right here, which is nice because our friction and our tension are going to line up on that x-axis. And we're going to define our y's perpendicular to that, which is how our normal force is going to be acting. So again, the only component that we have is going to be gravity. So how do our sum equations look now? All right, so when we look at the equations in the y direction, we've got the same thing. This is our force of gravity in the y. And our normal force. So that doesn't change anything. But in our x direction, we now have 3 forces. We have our force of friction, and we have our force of tension, and then we have our x component of gravity. Now this is still 0. There's still no acceleration in our y direction, but this is going to have some net force. So I should have written that over here. So we have some of our x forces. We have the force of friction. We do know what that is. We have our force of tension, which we know what that is. And then we have our force in our x component of gravity. And this is equal to some net force. So our friction force was, so let's look at this a little bit. Our friction force is going this way. So this is going to be a negative. Our tension force is going this way, so it's going to be a positive. Our x component of gravity is going this way, so it's going to be a negative as well. All right, this is a really nice thing to do to kind of help you keep those signs straight, because those signs are going to be important. So our friction force was 25 newtons, and that's just the magnitude. We know our direction is negative. So our friction force is a negative 25 newtons. We're going to add our tension force of a positive 150 newtons. And then over here we found our force of gravity. You don't necessarily have to do that again. It's going to be the same because it has the same mass. Our force of gravity was negative 147 newtons. And then we found that x component using that sine function. And so we found that that x component of gravity was negative 84 newtons. So this is the same because the mass hasn't changed. The only thing that's changed is our friction. So we have an x component of gravity of negative 84 newtons. Okay, and that's equal to our net force. So all we have to do there is just add those up. So if we take negative 25 plus 150 plus negative 84, we are going to get a net force of positive 41 newtons. So now we're going to come back and plug that in. Okay, we're still trying to find our acceleration. Acceleration is net force over mass. Our net force is a positive 41 newtons over 15 kilograms. So 41 divided by 15 is going to give us an acceleration of a positive 2.7 meters per second squared.